So, continuing where we left off, before we were so rudely interrupted, so we were talking about the schedule. So I was talking about the lecture, what is due on those particular days, so only the things related to problem sets there, and if you're reading along in the book, what pages to read by that time. So what I recommend is when there's a day that has a listing of pages to read them by that day. So don't read them afterwards. So lecture is just to reinforce what you already know by reading the pages in the book, if you're following along. So you'll notice some things are in yellow. And I think you might be worried about what those things are in yellow. So there are 2 midterms and 1 final. The final exam will be the entire 2 hours and 5 minutes of the last lecture. And the other 2 midterms, or the 2 midterms, will be the second hour. So I mentioned that we're doing this in 1 hour, 5 minute, then 1 hour block. So the midterms will be the second hour of that part. So they'll be 1 hour each. Okay?
And the stuff covered the same day, will that be on the midterm?
So what I guarantee is that the things covered by the end of the previous class will be there. So like, for example, Chomsky normal form will not be on midterm 1. If I cover it, whatever I cover that day in the first hour, it will not be on the exam. That'd be too ridiculous. Yeah, good point. Any other questions about the schedule? So as I said, I will be updating this, and I will let you know when I make updates. You can actually see at the top, I have a day where I say I last updated it. So if you have an older version, there is a difference, and I'll make sure to know where there are changes, if there are any. Yeah?
Is the final the entire 2 hours and some minutes?
Yes,
okay.
the entire time. Mm-hmm. Any other questions? Cool. So let's get started. So where do we begin? Many places we can begin. So what is this class called? It's called Intro Theoretical Computer Science. So you're probably wondering, what is the theory behind this computer science stuff? So you may think, well, okay, as being a smart ass answer, you probably might say, it's the theory of computer science or the theory of computing, okay? So that may seem like, okay, yeah, of course. But that actually gets us a lot of the way there to where we need to start. Theory of computing. So what does that actually mean? It's the study, because that's what theory means, of computing. So it's really the understanding of how computing fundamentally works. What does a computer really do? And try to model that in a theoretical way so that we can analyze in a theoretical way what that type of machine can do. So let's say that you are let's just say that you're a computer, for instance. What fundamental things do you actually need in order to compute something? Some kind of input, yes. So let's say that we have an input stream of bits or whatever. So let's say it's bits, whatever. What else do I need? A function or a computing unit, yeah. So some kind of black box that takes an input and computes something with it. So let's call it our computing unit, let's say. What else do we fundamentally need? Some kind of output. And we can say that this is an output stream. Okay? But do I really need an output stream? I do need some output. I need to figure out what actually happened in the course of computation. But you may want to have a stream. right? You may want to say, okay, I'm gonna output this string of bits at whenever I get this value. But what we're gonna do is we're gonna ax the stream and we're gonna replace it with an output bit. Oh, should learn to write correctly. Output bit. So a 0 or a 1. So I claim that this doesn't change the model, but it actually makes things a lot simpler because all we need to think about is input produces a single bit, a 0 or a 1. Or let's say accept or not accept. I accept this input in the case of 1 or not accept in the case of 0. What else do we fundamentally need? Well, we need some kind of internal data storage of storing maybe registers or some internal memory. So we need some kind of internal memory, right? But we're going to make something that doesn't seem like it's going to limit it very much, but it actually dramatically lowers its computing power. It's going to be a fixed internal memory. So, but you say, well, I can add more RAM to my computer, but there's an inherent max that you can put in, right? I can't add infinite memory to a computer. So I'm going to allow you to have a fixed internal memory, and you can't add more, okay? It turns out when we talk about adding memory on the fly as much as we want, that dramatically changes the computing power, but we'll get there in 4 weeks. All right, so we have fixed internal memory. Do I need anything else? I don't really think so. Secondary storage, as I said, we don't really need that because we can just up this fixed internal memory to some value that we actually need and never go beyond that. Do I need some kind of other input or output stream? No, because if I have multiple input streams, I can concatenate them together into one long input stream. So I don't need multiple input streams. We can do the exact same thing with output streams, and I said that we can reduce that to a single output bit. So this is actually all that we need. We don't need anything else to compute a function. So the input stream, that makes total sense. It's a stream of bits or whatever. Output stream, just a single value, 0 or 1. Some internal memory. So now we need to talk about what this computing unit does. And that's going to fundamentally change things. Or not change things, but define what the model actually is. So what does the computing unit actually do? So what does the computing unit fundamentally do? Exactly. It processes some amount of input and may do something to the output bit, maybe set some flags, whatever. It may change some of the internal memory, or not, maybe, but it may change some of the internal memory too. So what we're going to do is we're going to call a state of this machine is its memory configuration. Okay? So a state of the machine is the memory configuration. So I have some memory configuration at one moment in time. I'm going to read some input, maybe a single character, maybe more. And then I'm going to go to some other state. Maybe the exact same one in the case that I don't change the memory contents. Maybe I do change the memory contents, in which case I go to a different state. Okay? So the fixed internal memory then is the states of the machine, or the possible states of the machine. Okay? All right, so then now we just got to figure out, I'm going to be traversing these states as I'm visiting the input, or I'm reading the input, and once the input is completely read, I'm in some state, okay? So how do you think that output bit gets determined? Okay, so yeah, so what we need to do is we need to determine for each of the states in the machine whether if we happen to end up in that particular state, whether we say yes, we accept that input, or we say 1 on that input, or we say no, we don't accept that input, or we say 0 on that input. Okay? So we need some designation as to the states of whether they accept or not accept the input. Okay? We need some kind of qualifier as to say, yeah, if we ended up in that state, yeah, we accept that input at that particular time. Or if we're in this other state, we don't accept the input at that time. Well, when I fire up at that machine, what configuration am I in? I'm in some configuration of the memory, right? I don't know what that is. It's some configuration. So we need to have one state as the starting configuration of the machine. So also a designation to one state as to whether it is what we're going to call the start state. Because we could define a model in which we may randomly go to some other state as the start state, but computers, if you don't know already, are inherently deterministic. It may seem non-deterministic, but they are deterministic. If you execute the same program, it will do the exact same thing, okay? Given the same memory configuration and all that. If it's given the same memory configuration, at the start of execution of the same program, it'll do exactly the same thing. So computers are deterministic. So we need a special designator to one state. Okay? Any questions on this? Okay, well, we could, for the next 6 weeks, talk in this informal language, right? We could say, oh yeah, this machine does this, and blah, blah, blah. We need to be formal in this class. So, what do we need to do? We need to define a formal model of computation for a machine that looks and behaves like this. And then, at that point, now we can actually understand what this machine is going to do. Okay? So, let's talk about a particular machine, and then we'll actually define the model at that point. So what we're going to do is we're going to draw state diagrams. So we're going to be drawing state diagrams in which states are circles, and in order to go from one state to the other via reading some input, we're going to put some label on that transition, meaning once I'm in that start state, or whatever state I'm in, if I read that symbol, I go to some other state. So let's talk about this machine. So if you actually go back and read the original paper on how these machines were first defined, they use Q sub some number for the state number. The states can be named anything you want. It's just they happened and the tradition is to call them Q sub whatever. So, and by convention, Q0 is the start state, but any state can be the start state. There's no qualifier as to which one is the start state and which one isn't. So let's talk about this machine. It's going to have two transitions, two states, and what do you think that double circle on the right represents? Yeah, so a normal state is going to have just a single outline of the circle, And what we're going to call a final or accepting state is the one that happens to have two circles. So what is Q0? Is it accepting or not? Not accepting. That's pretty easy to see. What is that arrow coming from nowhere to Q0? What do you think that means? So that's going to represent the start state. So that thing is the start state. Okay. So Q0 here is the start state. So when I fire this machine up, I'm going to start in Q0. And what if I read a 0 in Q0, state Q0, where am I going to go? What state am I going to begin? Q1. Okay. And if I exhausted the input at that time, I read 1, 0. Now I've exhausted the input. What do I say to that input now? I accept it. Because, how do you know? I am in an accepting state. So let's make this a little bit more formal. So let's say I have the input 0, 0, 0. We will accept it. But before I've read anything, what state am I in? I've read nothing so far. I'm in the start state Q0. So here I'm going to put the state and input here. So what I'm going to do is I'm going to trace through the computation. It may seem a little trivial here, but what we want to do is understand fundamentally what's going on. So if I'm in Q0 and I see a 0, where do I go? Q1, like we talked about before. Nice. Have we exhausted the input yet? No. So I'm in Q1 now. What's the next input character? 0. So where do I go? Good. Q0. Have I exhausted the input? No. If I'm in Q0 and I read a 0, where do I go? Q1 again. Ryan, why are you boring us with this? Trust me, it's going to ramp up. So, have I exhausted the input now? Yeah. What should I say to this input? Accept. So I say accept 0, 0, 0. Okay? Can anyone tell me what this machine, what the strings this machine accepts are? Odd numbers of zeros. So we can actually check whether an input's length is odd using a model like this. It seems pretty simple. We only need 2 states. We don't need this gigantic C program or whatever. We can build something with 2 states. And the really cool thing is that I don't have to remember the past input. I only need to remember 1 character at a time and 1 state, which is really nice. Okay? Any questions on that example? Okay, so let's make it a little bit more demanding. We're going to have 4 states this time. Q1, Q0 through Q3. And we're going to have 2 possible characters on the input now. So either a 0 or a 1. So whereas before, we only had 1 possible character on the input, which was 0. Whereas here, we're going to have a possibility of 2 characters. So what we're going to have is 0s across, 1s down, oops, 1s around, ones up and down again, 0s. Okay. Are computers deterministic or non-deterministic? Deterministic. So the possible characters for this machine are 0 and 1. Should there be a possibility such as Q3 not having a transition on 1? No, because if I happen to be in Q3 and I see a 1, that's not deterministic. I don't know what to do at that point. So we need every state to have every possible transition coming out of it. So the possible symbols are 0 and 1 in this case. So we need every state to have a 0 transition going out, or maybe coming back to itself, and a 1 transition going out, or maybe coming back to itself. And so what are the strings that this machine accepts? None. There's no string accepted by this machine. How can you tell? There's no final state or accepting state. So let's make this a little bit more interesting. Let's make those two final. Can I make all states final? Yeah, it might be a pretty stupid machine at that point, right? But it's a valid machine. It's completely valid. It just does, it accepts every possible string. What about for this machine, the empty string? The string that has no characters in it. What does that do? It does absolutely nothing. So we do not accept. What's a string that this machine does accept? Yeah, 0 and 1. This thing accepts. Yeah, so what's another string that it does not accept? Preferably landing in Q3. 1, 0, yeah. So that's one string it does not accept. Okay? Yeah.
How is the input stream 0, 1?
Those are two separate lines. Yeah, I meant, yeah, I should be more formal. So 0, do not accept. Oh.
0 individually is accepted, 1 is individually accepted.
Thanks. Accept, 1, same. Yeah, you're correct. Any other questions about this? So what do we know so far? What we want is that this machine has states. It's deterministic in the case that every state has all possible transitions coming out of it. There's a denoted start state. And there's a possible set of what are called final or accepting states. It could be everything, or it could be nothing, or anything in between. So let's make this formal. But any questions about this example or anything previously? Okay, so let's make this formal. So, and also, can the number of states be infinite? We could define the model that way, but we're trying to model a real computer. How many states could a possible machine have? Finite. It's a humongous number, but it's still finite. So, a deterministic finite, I love this name, automaton. The original paper, I'll post it on Blackboard, also called these deterministic finite automata, is a something tuple. I'll get to that in a second. So this is where the map 243 is going to come back. So we got to define the set of states. And before we had them be Q sub whatever, they could be named anything. But the convention is to use Q, so it was lowercase q before. What is it here? Capital Q. Q. So there's going to be more stuff behind it where Q is a finite set of states. Okay. So just what we were talking about previously. What else do we need? Yeah, so in those two examples, one of them had the set of input characters being just 0 for the first one, and the second one had 0 and 1. So when we're talking about, say, a actual CPU, it only really does take zeros and ones in. But could I be talking about a model where it could have anything be as input? Yeah, possibly. I could have maybe 10 different possible characters that could be on the input. So let's make this as general as possible. So I'm going to allow you an actual arbitrary alphabet. So sigma is a finite alphabet. So all it is just a set. It's just a finite set. So in the case of the previous examples, sigma in the first one was the set containing 0, and the second one was sigma is just the set containing 0 and 1. Nothing fancy. But I'm allowing you any set, any finite set, as being the input alphabet. Okay? I should move that down a little bit. Anyone else like notability? I like notability. All right. What else did we need to do in this model? Yeah, we needed to have that arrow coming in from nowhere. We need some state to be denoted as the start state. So I'm going to skip one for now. I'm going to call it Q0. The name means nothing as long as it's an element of this set Q. So Q0 is an element of Q, and we call it the start state. Okay? Oh, I should mention one thing. This class moves rather fast, so if you need a minute of catching up to do in your notes or whatever, I'm happy to give it. Okay? Please don't do it 30 times in a lecture. But if you need like one or two times, please ask, and I'm happy to grant it. I understand that this is a lot to take in, so if you need it anytime, please let me know. So because the tendency, if no one asks questions, my tendency is to go faster because I assume everyone understands it. And that's the worst thing to happen in this class. Okay? So yeah, don't fall behind. Okay, what else do we need? Yeah, we need some states to be denoted as the accepting states, right? And as we said, could it be the case that no states are accepting? Yeah, could all states be accepting? Could it be some arbitrary subset of the set of states? All right, so we're going to put this last component in, called F for final. I don't know why they did F for final, but not S for states. I don't know. Notation's weird in this field. So F is an arbitrary subset of Q. So this is the set of final states. Okay, so it's just an arbitrary subset that you feed into this machine. Feed as the description of this machine. What did I forget? Yeah, the way that we transition between the states. Okay, so we need some formal way of saying, okay, if you're in this state and you happen to be reading this input symbol, you go to this state. I'll ask again, are computers deterministic or non-deterministic? Deterministic. Okay, so let's say that we have a fixed state and we have some symbol that we are going to read. How many states should I allow you to go to? Should I allow you to go to 2? No, because then you'll have to make a decision as to which one you're going to do. Okay? So we're going to allow you to go to exactly 1 state. Okay? So this middle piece we're going to call delta. And so delta, I'm going to define it down here, is the transition function. Of the machine. Yeah, go ahead.
I'm confused about Q versus sigma.
Yeah, what's your doubt? What's your doubt?
Like, I guess I don't exactly understand what sigma is.
Okay, so it's just the name of a set. That's all. So I'll go back and we'll formally define the previous machines. But all it is just a set in both cases, and yeah, it's just a set in both cases. And it can be as arbitrary as you want, yeah, as long as it's finite. Some other question? Are there any other questions before I formally define delta? Okay, so computer's deterministic or not? It's important to understand. So, should I ever have the possibility of having some state and some input symbol not go somewhere? No. Should I ever have the possibility of having some state and no input symbol associated with that state on a transition? No. So I should have every possibility of every state with every input symbol goes to one state. Okay? So delta is just a transition function, so it takes in a state and an input symbol and it outputs a state. So let's just write that as a function. Delta is a function from Q cross sigma goes to Q. What that means in English is you provide a state to me and you provide an input symbol, you output a state. Okay? You actually output exactly one state of Q. Does this say that every pair of state with input symbol is defined? No, it just says that it's a function, right? It doesn't have to output something. It doesn't have to be defined for some state and input symbol. So we need an extra qualifier. We need to say that delta is a total function. And I am very, very, very aware. Pretty much none of you have seen this term. So what total means is that every every state and every input symbol is defined. That's all it means. Okay? So in order to make this deterministic, every pair of state with input symbol is defined with exactly one state. Okay? Yeah, I'll repeat it again. So delta is a total function. What does that mean? It means that every state and every input symbol is matched with exactly one state. And I'll show you how that works with an example to make this more clear. Yeah. It's not a bijection because you don't necessarily have to hit every single state. Yeah. Yeah, it's not a bijection because it actually wouldn't work if sigma was any alphabet of size larger than 2, because anything times 2 in size is strictly larger than the original thing. So it actually wouldn't be a bijection in that case. So it's not a bijection. Any other questions? So I will do examples, don't worry. Okay, so let's go back to our previous examples. So let's copy this. Man, I love Notability. So let's go on a new page. So we have this first machine. So we need to so now let's do the formal definition of this guy. So we need to, in order to formally define this two-state machine, we need to formally define it. So how do we formally define this thing? Well, we gotta define all 5 parts. So I'm gonna skip delta for now. I'll get back to it. So what is Q fundamentally? Is a finite set. Okay, so I need to write a set notation here. So what things are in Q? Q0 and Q1, the states of the machine. Okay, so Q is just Q0, the set containing Q0 and Q1. Okay? It's just a two-element set. Nothing special about it. It's just a two-element set. So what is the fundamental structure of sigma, the second piece? It's also a finite set. Okay, so sigma is also a set. What does it contain? Just the element 0. Okay. What is the start state of the machine? Q0. So it seems kind of silly, but it's important to understand that Q0 equals Q0 means that that the start state of this machine, as denoted in the picture, is called Q0. And what is F in here? What is the fundamental structure of F? It's a set. Because why is it a set? It's a what of Q? It's a subset of Q. Okay? So F is a set as Q was. And what are the elements in F? Just Q1, and how do you know? Yeah, it's the only final state in that original machine, so Q1. So, have I defined all 5 parts yet? No, so what do I need to define? Delta, the transition function. So, there are two, did you have a question? Okay. Are there any questions so far? Okay. There's a lot of you. All right. So there are 2 modes of thought in order to define the transition function. So my favorite and the easiest way I recommend to all of you is a transition table. Okay? So we'll do both for completeness. So transition table. So there are many ways that you can approach this. So I'm going to show you how I do it. So I'm going to have my left column represent states of the machine, and the things representing columns being the symbols of the machine. What are the states of the machine? Q0 and Q1. What are the symbols of the machine? Yeah, just 0. So there's only one column here. So we'll see this in a second, but what does total function mean in terms of this table? Yeah, every single entry in this table is filled with exactly one state. That's all it means. Okay? Every row and every column has exactly one state in it. Okay? So what should I put in the entry for Q00? Q1. And Q1, what should I put in its row? Q0. Okay? Nothing fancy. It's just straight up copying what's in the diagram into a table. Okay? Any questions about that? Okay? Well, as I said, there's another way of thinking about it, and I don't recommend this, but it's even more formal, so I can't disagree with it, because I'm formal. So what we could do is define it as the transition function itself. So what we need to do is write delta of, well, what does delta take as input? What are the 2 things it takes? Current state and input symbol. So we got to fill 2 things in delta. So one combination will be Q0 and 0, and the other combination will be Q1, 0. What does the transition function output? Just a single state, right? So this transition function equals what? Q1 in that particular case, and this one is Q0 in this case. Okay? So the table is much more compact in my opinion, even though I didn't draw it that way. But in general, it's more compact. I recommend it, but both are equally valid. Any questions on how we formally define this thing?
Is there any benefit of doing one versus the other?
Not really. So if I ever asked to give a formal definition of some these things are called DFAs, deterministic finite automata. If I ask give a formal model of a DFA, either one's perfectly fine. Yep. Any other questions? Okay. So what else did we do with this machine? What else did we look at? Yeah, what kinds of strings it accepted, but we'll get there eventually. But what types of things did we look at first? What things did I present you with and we said, okay, yeah, it did this, and then it did this? Yeah, so yeah, let's look at what we did. So we looked at the input string 000 in this particular case, and we said, yeah, you start in Q0, and on this input, you go to this state because we follow the transition, and then once we're in that state, we follow the next transition, and then when do we stop? When we run out of input. Okay, well, do you think that's fairly formal? No, so let's make that a more formal thing. So these things are called computations. So a computation of, so now I can't define it for the two DFAs that we just did, or just give you a small example and say, yeah, that's going to work for all DFAs, just think about it a little bit. I don't think that's very formal. So we need to give this for every possible DFA that exists and every possible string that exists. But before we get there are a few things that we need to worry about first. So we talked about, from the example before, that this DFA accepts only the strings that have odd length and consist entirely of zeros. Okay? Well, what about all the possible strings that exist? We may need to talk about those because, as I said, when we talk about computations, we need to talk about every DFA and every string. So we need to say, okay, what is a possible string that could be defined for this DFA? Okay? We need to give some notation for that. So let's let sigma be an alphabet. And what we're going to call sigma star is the set of all strings over sigma. So just as an example, if we have if sigma happened to be the set 0, 1, sigma star is the set of all binary strings. Okay? But, of course, we can talk about any alphabet here. What if sigma was the empty set? What is sigma star in this case? Well, could I ever pick a string of length 1 or more? Could I pick a string of length 0? Yes. Pick 0 things out of the empty set. What string do I have now at this point? The empty string. So sigma star happens to be the empty string in that case. Is sigma star always an infinite set? I just showed you one that isn't. But other than that example, where it's the empty set, is it an infinite set? Yeah, because if we have any character in sigma, I can just repeat that as many times as I like, any finite number of integer, any finite number of times, and therefore I can have infinitely many strings. Okay? So other than that case, sigma star is always infinite. Any questions on, yeah?
Is the empty string like a standard notation?
Yeah. So there are other textbooks that have lambda as being the empty string. So there will be something about this in problem set 1 related to this, but empty string, so epsilon, so this is called epsilon. That is the empty string. That's the standard notation that we'll use. But I've seen and have had a class with lambda being the empty string. Yeah. Any other questions? Yeah.
On your sigma, are you using the subscripts and superscripts, or is that just the way you're
Oh, where's the supposed subscript?
Is it sigma 1, 1?
So I like putting the little pointy parts on sigma to make it look nice. Yeah, because I've had plenty of comments of having my sigmas look like E's. So I put those to make it very clear, or as possible as to be clear, to be sigma. Writing is difficult in this class. Yeah, so that, do you see why now I say please type your problem sets? Yeah, because I've TA'd this class 3 times and I still have trouble. So type if you can. But any other questions otherwise?
I have a question.
Yeah.
When you say that sigma star is the set of all binary strings, what does that mean?
Yeah, so all the strings that have zeros and ones. So like, as an example, 0, 1's in there, 1, 1, 0, 1, 0, 1 is in there, all binary strings. It's what we colloquially use as the set of binary strings, but it's just the set of all strings that happen to have 0 and 1 in them. Okay? Any other questions? So now we're ready to talk about a computation on an arbitrary DFA on an arbitrary input. So let's let M, I should say, of a DFA M. So I don't know, since this is an arbitrary DFA, I don't know what the structure of M is going to be. So, but I know that it is a DFA. So I know that it has 5 parts, Q, sigma, delta, Q0F. And now that we understand or at least some of us understand the notion of sigma star, we know that there is some string in sigma star, but I don't know what string this could be. It could be any string. So we gotta say, and a string W in sigma star. So we got to say what this computation thing is. So it really helps to go back to our example. So let's go back to the example with the 3 zeros. So if you're writing a program and you want, let's just say that your friend says, okay, yeah, you tell me that you computed this thing, but I don't believe that you actually did. What would be your proof to him that you actually did do that computation? or in like a C program or whatever, or anything. How would you prove that to him?
The output.
Well, the output, but that could be that I just happen to know it instantly. I didn't actually go through the computation. Okay, so maybe I can look at what transitions were taken. But we already know what the transitions are, right? They have some label on them. If I give him the sequence of states that I travel through, and along the way, make sure that the transitions behave accordingly with my input string, then that's a valid computation. And he says, yeah, I believe you. Okay? So let's see. We have 3 characters in this input here. How many states did I visit? 4. But you say, no, there are only 2 states. Can I visit a state more than once? Will you let me? Okay, so how many states did I actually visit? 4. Because we started at 1 right at the beginning. We haven't read anything. We visited 1 state. I read 1 character. How many states have I seen? 2 in total. Read 1, now 1 more character, so now 2 characters. How many states have I seen? 3. If I've read n characters, how many states have I seen? N plus 1. Oh, wait. What if W is the empty string? How many states will I see? 1. Because I won't ever execute a transition in this model. Yeah. Yes, absolutely, yeah. So I could have defined this. Let's define it here. So great question. So what if instead of, I shouldn't have gotten rid of that one. Let's keep this one. And so this looping arrow that comes back to itself, that's what is called a self loop. Okay? So in this modified DFA, what are the strings that it accepts? Just as an exercise. At least 1 0. Or, equivalently, what's another way to say it? Not the empty string. Okay? Any string that's not the empty string. Okay? Cool. So, if W has n characters, how many states will I see? N plus 1. Because if I've read 0 characters, I already have seen the state because I had turned on the machine. So I gotta say where the length of W is n is a sequence of n plus 1 states. Well, do I know the names of these states? No, because it's an arbitrary DFA. It has arbitrary names on its states. I don't know what the states are, but do I know that they are states? Right, that they are states. As long as I give some qualifiers on what they can be, then I can actually give names to them. So it's a sequence of n plus 1 states. So let's give the sequence. I'm going to call them R0, R1, R2, dot, 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 up to R sub n. And I've named it for that reason, with those subscripts for a reason. So it's n plus 1 states because I start at index 0 and end at index n, so there's n plus 1 of them. Well, should this be the definition as is? Well, it's just a sequence of n plus 1 states. It could be any sequence of n plus 1 states. Is that true in our model? Could it be any sequence? No, because it's a deterministic machine. So we got to put some qualifiers on what the R sub states could be. Well, where? What is something that we must know about this sequence? I'll give you a hint. It's about R0. What do we know about it? It's the start state of the machine. It has to be. I have to start in the start state always. Okay? So R0 is start state, and we called it Q0. So we know that R0 equals Q0. Okay, well, that got us one state in the sequence, but now I need the other n states. How am I going to figure out what those are? Well, let's get a small example first. Well, partial example. How do I get R1 from R0? It's the output of the transition function from what state and what input symbol? The start state, which happens to be R0, so the thing right before it, so that's good. But what thing am I actually reading? Which character of W? And so now I got to actually give some names to the characters of W. So I got to say W is W1, W2, up to Wn. So now I've actually, I should say, and each Wi is in sigma. So each of these Wi's is exactly one character. Okay, so in our previous example, it was W1 is 0, W2 is 0, and W3 is 0. Good. Well, in order to get R1 in this sequence, I got to go from R0 on some transition to it, but what transition? What thing did I read? Well, I got to read some character of W, W1. I read the first character of W. Okay, so I'm just going to put this in as a side note. So R1 happens to be the state that we get out of seeing the transition function on R0 and reading what character? W1. Okay, so like in the previous example, R0 was Q0, and R1 in that case was Q1. So Q1 is the result of transition function from Q0 reading a 0. Okay? How do I get R2? Ah, yeah. So remember how we were computing before. I only needed to remember the previous state in order to know the next one. So the only information I need to know to get R2 is R1. And what character did I read to get there? Ah, yeah, W2. Let's generalize. How do I get R sub I in general? I only need to know R of I minus 1 with W I. Good. So we can fulfill our second condition now, where R sub I equals delta of R sub I minus 1 Wi. Sweet. But I gotta say for all I at least 1 to n. Oh, not a comma. Because I can't just say, okay, yeah, one of the transitions worked, but none of the others did. I gotta say every transition in this sequence not only is in the machine by the transition function, but also obeys the input that we actually read. Okay? So let's recap. I have an arbitrary DFA and some arbitrary string in its alphabet, or of characters from its alphabet. It's a sequence of states that we see. That's informally that we want to have. So I must start in the start state, and I must have that every single time I go on one transition, I consume a character of the input, and I go to the next state, I go to the next state, and I must stop at when I've actually read the last character. When I've read WN, I go to RN. Okay? But something pretty important that will come up later. When I read a character, can I go back? We could define a model that behaves like that, but in this case, what happens is, via this formal definition of computation, we do not ever go back. Once we consume a character, it's gone forever. Okay? Perfect. So this is a computation of any machine, any DFA, on any input. But maybe we want to talk about the ones that are actually accepted by the machine, right? Because sometimes, like for the previous example, we talked about that it recognizes the strings of length, this modified one of length at least 1. And before we modified it, we talked about how it was accepting exactly the things of length that are odd, right? Maybe we want to talk about that instead of just, okay, yeah, 0 star in general. So this is just a normal computation on any string, but sometimes we talk about an accepting computation. Of same machine on W. Well, it better be a computation. And let's just say it is R0 up to Rn like we did before. It's just this sequence of states. But like we did before, we said, okay, yeah, we accept this particular input, or we don't accept this particular input. So if I want to say that M accepts W, what is the extra qualifier that we need to add?
The RN is the unaccepting state.
Right, so Rn is in the set of final states. So I need to say, and R sub n is in F. Yeah, so like before, we checked that we accepted the string 0, 0, 0 by seeing that we ended up in state Q1, so that was Rn in that case. And we said, oh yeah, Q1 is in this definition of F. So therefore, we should accept this string because not only have we run out of input, but it's also a final state. Sometimes we talk about what are called rejecting computations, where Rn is not in F, or not accepting computation. Any questions on this? As I said, please don't follow behind, because this stuff builds on over time. Okay, so as I said, we may want to talk about, say, the strings that are accepted by this machine, like in the previous unmodified example, the things that have odd length. So now we will define the language of a machine. So the language accepted, another term is recognized, is exactly the same thing, by a DFA M with the 5 parts is, oh, I should say, so the notation that we'll use over and over and over in this class is L of M. So the language of this machine M. So how do you think I should formally define this thing? Exactly. The set of all strings in what? Sigma star that have an accepting computation on M. Oh, well, M has an accepting computation on M. Is this set. If the set W in sigma star such that M has an accepting computation on W. I know this is definition city here, but it's important to understand how this works. So M has an accepting computation on W, means we accept it, so therefore we put it in this set L of M, so the language of M. So it's just all the strings that this machine happens to recognize. Okay? Okay? And we'll do an example, I promise, if we have time. Yeah, you have a question?
Does the phrase the language accept and recognize mean more?
I was going to ask that. Great question. How many computations can a DFA have on an input? One. Could it have two? No, because it's deterministic. Can it have zero? No, because even the empty string always will start in the start state. It must have at least one state in its computation. So it has exactly one computation. Every string has exactly one computation. How many accepting computations could there be? Could there be one? Yeah, it may accept the input. Could there be two? No, because if there aren't two computations, there's no way to have two accepting ones. Could it have zero? Yes. Because, like in the previous example, if you never went to the final state, there's no accepting computation for you. You will always reject on your only computation. So the number of computations always is 1, but number of accepting computations can be either 1 or 0. In the case of accepting for one and not accepting for the other, for 0. So here, we didn't really talk about this word language. So what do you think language means in a formal way? Yeah.
Subset of strings?
Yeah, it's just a set of strings, right? So a language in general is a set of strings. All it is a set. Can a language be finite? Yeah, because in the case of maybe you accept 0 strings or 1 string, that's definitely a finite set. Can it be an infinite set? Yeah, in case if it was like all of sigma star where sigma is non-empty, like in the case of that last example, way over here, we accept every string that's not the empty string, and in this case, there's infinitely many other strings, so the language of this machine is infinite. But it could very well be finite. Okay? So one more definition, I promise. A language L. So when we're not talking about a machine, we usually say a language L, but I can call it whatever. is called regular if it is accepted by some DFA. So let's just go over a few examples. So the one we talked about in the modified example was sigma star without, so set minus, the empty string. So that was from the example that we had. Can I say that whether that language is regular or not? Yeah, how do you know? I built a DFA for it. It really is that simple. If you have a DFA for it, its language must be regular because I called it regular. Okay? So this is regular. What about sigma star? Is it regular? In other words, can I make a DFA that accepts everything? Yeah, it's actually pretty simple. So whatever I do, I loop on everything. It's a pretty stupid DFA, right? But I accept everything. So its language is, well, it's regular, but what is it? Everything informally that's called? Sigma star. Good. What about the empty set? Is it regular? Could I build a DFA for it? Yeah, I could very well make a DFA just like the last one, but I just make it not final. Okay. Does that DFA right there, does that accept anything? No, because there's no final state. Okay? Since it has no final state, it must accept nothing, so its language doesn't have any strings in it, and therefore it's the empty set. Okay? So the empty set is regular as well. What about the set containing just the element 0? Just that single string. Yeah, that's also regular. How do you know? We already made an example for it. So see above. So that's also regular. So for roughly the next 2 weeks, we're going to be studying regular languages and what properties that they have. And then at some point, so I'll give you a little outline of the class. So we're going to be studying regular languages for a while. And then at some point, we're going to say, oh, there are some languages that are not regular. So there's no DFA that could recognize them. Okay? And then we'll, at some point, once we do that, go to something called the context-free languages. So informally, we had a DFA that had a fixed finite memory. In this model, for context-free languages, we can have a stack, which means that you could, in principle, have some amount of infinite memory. But it turns out we'll see languages that are not context-free either. So then we'll, again, generalize and talk about Turing machines, which is a generalization of both DFAs and the model for context-free languages. And then we'll talk about languages that are decidable, which means the languages that is a model for your computer that can be recognized in a finite amount of time. And we'll look at that for a while. And then we'll realize there are languages that are not decidable, in a case the halting problem is one of them. Okay? Are there any questions? So, I'll see you on Monday.